In this video, we'll examine conjugated dienes and their molecular orbitals. Before we get into the conjugated dienes and its molecular orbitals, let's first go back and review molecular orbital theory just briefly. So molecular orbital theory is a description of covalent bond formation that results from a mathematical combination of atomic orbitals to form molecular orbitals. So essentially it's taking our two atoms and the orbitals associated with those atoms and showing how they combine together to create a bond. When they combine together, we get two different types of orbitals. We get our bonding molecular orbital, and the bonding molecular orbital is always lower in energy than the atomic orbitals. We also create anti-bonding orbitals. These are molecular orbitals that are higher in energy than the atomic orbitals. And so if we look at combining two 1s orbitals together, when they combine together, they create a sigma orbital that's bonding, and then an anti-bonding orbital that's still a sigma. And the anti-bonding orbital is usually designated with a star. And so this would be an example if we took two hydrogens and created an H2 molecule. And you can see the sigma bonding orbital is lower in energy than those atomic orbitals. The sigma anti-bonding orbital is a higher energy. Also note that the higher energy anti-bonding orbital has a node that runs through the two atoms. So what this indicates is that the electrons from this atom are separated from the electron from this atom. And with our molecular orbitals, we always remember when we start with two atomic orbitals, we should get two molecular orbitals. Same thing if we start with 4 atomic orbitals, I should get 4 molecular orbitals. So the number of atomic orbitals we start with is the number of molecular orbitals we obtain at the end. So now let's look at forming pi bonds using molecular orbitals. With our pi bonding molecular orbitals, they're a combination of p orbitals. And when the p orbitals overlap with the same algebraic sign, so plus or minus. And the anti-bonding orbital is a combination of lobes with opposite signs. So if we look at our p orbitals here, so if I have two p orbitals, I'm going to get two bonding orbitals out of it. From two p orbitals, I get a pi bonding orbital and a pi anti-bonding orbital. So we get our pi star anti-bonding and our pi bonding. And you can see if we consider red the plus sign and blue the minus, and the bonding, the two minus signs overlap, and the bonding, the two plus signs overlap to create a continuous electron system on top and bottom. In the anti-bonding one, you can see we have our minus next to our plus, which means there's no electron overlap between these. So we have a node that runs right through the two atoms again, indicating that a bond is not formed. If the two orbitals can overlap, then that indicates it's forming a bond. And since we know pi bonds have electron density on top of the atom and bottom, that's why we show it like this. And so if we look at the pi bonding system for ethylene, we remember ethylene looks like the structure drawn here, C2H4. And if we focus on just the pi bond, so we're focusing on just the pi bond molecular orbital, that has to form from the two p orbitals. When that forms, each carbon brings in 1 electron from its p orbital. So we start filling from the lowest energy orbitals up to the top, which means with ethylene, we'll put both electrons into that lower pi bonding orbital, and that pi star anti-bonding orbital is left empty. And so one important thing is that a molecular orbital extends over the entire molecule. So we can extend this out beyond ethylene. If we look at an extension beyond ethylene, look at butadiene, which would be something more similar if we had this, where we have double bond, single bond, double bond. So we have a conjugated system here. So if we look with our conjugated system for butadiene, we can see each carbon is going to give one electron from its p orbital. So each carbon in the chain here has one p orbital and one electron in that p orbital. And so that means we have 4 atomic orbitals. Since we have 4 atomic orbitals, that's going to equal 4 molecular orbitals. And so our 4 p orbitals can look something like this. And so when we start to fill it up, we start at the bottom with our most stable system where there's full conjugation across all 4 atoms. Then we draw our next orbital where there's only one node between the 2 double bonds, so they act like they're an isolated system. In the 2 nodes, so this one would have in the 2 nodes, there's 2 breaks in our molecule, and only in the middle do we have a conjugated system. So we have that pi bond in the middle. With our 2 nodes, we actually end up with just the pi bond between the 2 middle carbons. And in 3 nodes, there's no overlap, which means there's no pi bonds whatsoever in the molecule. So looking at the orbital overlap, with the most stable configuration where they're all connected together, we can see we'll put 2 electrons in there. And then we have our 1 node where they act like they're 2 isolated double bonds. And that will get 2 more electrons. And then the 2 nodes with our double bond system in the middle, that actually doesn't have any electrons in it. Same thing when there's 3 nodes, so no conjugation whatsoever, no pi overlap whatsoever. We don't have any electrons. And so when we're drawing our molecular orbitals, each time we go up an energy level, so we go from 1 to 2 to 3 to 4, we're adding 1 node. So always start with 0 nodes and add 1 at a time as you go up in energy. And so let's look a little closer at these. With our 4 pi electrons in butadiene, it'll occupy the lowest energies of the molecular orbital. That makes our molecule more stable. That's how it affects the stability. I have the electrons in the more stable configurations of the molecular orbitals. It infers more stability on our molecule. And then the one where they're fully overlapping, that's actually a more stable configuration than in the one where there's 1 node. So in the one where there's 1 node, there's no double bond character in the middle here because it's not a constructive overlap. I have a plus and a minus sign. Since I have a plus and a minus sign, they're different signs, so there's no overlap. With the most stable configuration, we can see on the top, they're all minus, and on the bottom, they're all plus. And so this molecular orbital theory also can explain why that central carbon-carbon single bond is actually shorter and stronger than a typical carbon-carbon single bond. So if it was a typical carbon-carbon single bond, it'd be like our system with 1 node here. But since we also have this structure and this electron configuration adding to our molecule, that's considered more of a double bond character. So that's why the carbon-carbon bond here is actually a little bit shorter carbon-carbon single bond. And we don't really look at the other 2 molecular orbitals because there's no electrons in them. They don't add to the electronic structure of our molecule. So now let's look at one slightly longer. So we're going to look at 135 hexatriene. Which looks like something that I have drawn here. So there's 3 double bonds in our conjugated system. Since there's 3 double bonds in the conjugated system, there's 6 carbons in it, which means we have 6 pi molecular orbitals. So we take our 6 p orbitals and we start combining them together. We start at the bottom with our lowest orbital, where all of them are in the same phase. So we have full conjugation across all 6 carbons. Then when we go up in energy level, we add 1 node. So we're going to add 1 node right in the middle. So I have 3 carbons conjugate on one side, 3 carbons conjugate on the second side. Then we go up to the next level where we get 2 nodes. So when we add 2 nodes, we have conjugation, 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 separated by 2 nodes. This one kind of looks a little more like what we typically draw in our skeletal structures. Then we go up to the next level where we don't have any electrons in it, and we add 3 nodes. So we have lone atom, double bond, lone atom. We can go up to our 4th node where we have lone atom, double bond, lone atom, lone atom. Or a 5th node where they're all separated and there's no conjugation whatsoever. So you can see as we go up in levels here, we go from more conjugation, more electron and orbital overlap to less and less each time. Less and less atoms are overlapping each time we go up a level. And so when we look at these molecules in our molecular orbital diagrams, we want to start defining things. We want to figure out what the HOMO and LUMO levels are. So HOMO stands for highest occupied molecular orbital. And LUMO, lowest unoccupied molecular orbital. So if we look at our hexatriene here, the highest occupied molecular orbital is the one with electrons in it. It's the highest orbital where the electrons exist. And the LUMO is the lowest unoccupied, so it's the one right above the HOMO. The reason we care about figuring out where the HOMO and LUMO orbitals are is they come into play when we actually do chemical reactions. When we do a chemical reaction, the HOMO orbitals of one atom interact with the LUMO orbitals of another atom to create a new bond. And so we'll see this a little later on when we start talking about Diels-Alder reactions and pericyclic reactions. And so looking a little closer at these frontier orbitals, the HOMO and LUMOs. If we're trying to do a reaction and the orbitals for our compound and the orbitals for our 2 compounds don't overlap properly, we can always change what the HOMO and LUMO orbitals are. So let's say we want our atom here, our hexatriene, to react with some other molecule. But the other molecule might actually have where the bottom orbital is our plus sign, and the top orbital is our minus sign. So if the orbital of our compound that we want to react is not in the same phase as the frontier orbitals, as the HOMO orbitals of our compound here, one thing we can do is I can take the electrons from the HOMO level and excite them up one energy level. So if we use light, that can excite an electron from a lower energy state to a higher energy state, just like you learned about with general chemistry. If you excite an electron with light, it jumps up in the energy levels. Same thing happens with our organic compounds. So if I jump it up, now this becomes the HOMO level, and the one above it becomes LUMO. And so if the 4 here, the level 4 state is the HOMO. Now, this is a blue one. It's the same phase as my compound that I'm trying to react with. Since it's the same phase on top and bottom, we can get a reaction to occur. So that's why it's good to know what the HOMO and LUMO levels of a compound are when you're doing pericyclic reactions or Diels-Alder reactions. So now you should have a little bit of an understanding about molecular orbitals and be able to draw a molecular orbital diagram for a conjugated system. Remember, with your diagrams, you always start at the bottom with the most stable configuration and 0 nodes. And each time you go up a level, you add 1 node to your structure. And then we typically use our shorthand here where we just draw the p orbitals and assign plus and minus to each orbital as we're going up in our energy levels.